Hello and welcome to the session. In today's session, we will be discussing about Huffman Code. But why do we need Huffman Code? What it is? That is what we want to discuss. So let us first try to understand the data transmission process which requires this Huffman Code. Well, data transmission process requires transfer. Basically, it transfers textual data as a sequence of characters. And each character can occur multiple times, and that means there is a frequency associated with each of this character. And as it goes in computer, that every character is represented with the help of some code. Now, the total size of the code is a code multiplied by the number of characters, right? That forms the total size of the transmission or data transmission system. Now that if we can minimize, if we can compress, then we will be very happy to do so, because our load of data transmission is going to be reduced. And that is where we use Huffman Code. Fortunately for us, Huffman Code is once again a greedy approach and tries to reduce the number of bits which are to be transmitted in a data transmission process. Let's take a very simple example which is going to explain this whole overall system. So let us consider a data file of just 100 characters to be, this may be very small data file, but this small data file will also explain us that how big the advantage of utilizing some compressed code like Huffman Code is going to be. And what we are having, the second thing we are having, 100 characters, and frequency of different characters is different, right? So, for example, the slide shows that there are fixed length character, right? So, 100 characters, and the frequency is somewhere like A is having 70, okay? B is having around 2 characters only in that overall code. C is having 5, D is having 13, E 3, and F 7. So this is the frequency of each of these characters, right? And suppose we code these characters with the help of ASCII codes, right? That is American Standard Code of Information Interchange, which is the standard code which we use to represent the character. But this is in the data transmission process, right? So how big the data transmission is? Since ASCII code, the standard ASCII code happens to be 7 bits. So the total number of bits, if you see, has been computed and put over there. The number turns out to be 700 bits, right? Because 70 characters, right? 100 characters and 7 bits per character makes it 700 bits which are to be transmitted. Can we improve upon this particular situation? Well, let's try to see any other option over here. So option 2, now how many number of characters are we transmitting? We are just transmitting 6 characters, right? So can we code these characters in less number of bits? Technically speaking, yes. Why yes? Because just 3 bits are sufficient to code this particular character stuff. And you can see in the slide, like A we have coded with the help of 000, B we have coded with the help of 001, C with the help of 010, D like that, right? D, E, F. So everything we have coded, and we multiply it with the frequency of each character, and ultimately it turns out that we require 300 characters. So from 700 characters, we have brought down the number of bits which are required to transmit this particular message, which consists of 100 characters. Now the question is, can we do still better than that? Well, that is where the need of Huffman Code comes in, right? Okay, so what is Huffman Code? Well, let's first understand the basic principles which are related to Huffman Code. First and the foremost thing which it tries to do, it reduces the number of bits which are to be transmitted. Okay, so even it should be less than 300. That's what we are saying. If we use Huffman Code, the number of bits are going to be even less than 300, which was the last case. Then what does it do? So on what principle it works? It checks the frequency of each character and represent the characters with high frequency using smaller code. So that is the idea, that if the number of times a particular character is occurring in that particular code, large number of time a particular character is occurring, represented with the help of very small code. But if it is occurring for less number of time, we can take the liberty of representing this particular character with larger data. Okay. Then length of the code of character will be variable. Now this is where it's going to be differing from 3-bit which we utilized, right? So 3 standard bit we use for everything, but A was happening or A was occurring for 70 number of times. So can I just code A with the help of 1 bit? And what should be that bit? Right? So that is the question which we have to answer. So there has to be variable length code for each character. Okay, so how will we design that code? That is the process which we are going to discuss in the Huffman coding. The decoding of message, right, should be unambiguous. So we can do a lot of coding as sequences, but the decoding should also be unambiguous. There should not be any loss of information, right? So the decoding process should be simple as well as unambiguous. So code should be like that. And finally, one more point which we would like to say, that Huffman code definitely compresses data by on an average 70 to 80%. Not necessarily the case which we are discussing. It may be 40 to 50%, but then in general it compresses the data to the extent of 70 to 80%. Now, what is the process of Huffman code? Now, the process involves that the prefix of a code should not be same for the codes of 2 different characters. Now, what do we mean by prefix? Like prefix means with which the code starts. So we will look at this term prefix when we look into the example also. But there is one example over here. That is, if 10 is code for, let's say, an alphabet A, then 101 cannot be a code for B. What is there? Because 10 is common between A and B. So it is the prefix of second code. Now this prefix thing is going to cause ambiguity when we are decoding. And that is why we will not allow this kind of a system. Now this ensures that while decoding the encoding message, that is the prefixing, right? No prefixing of the code. It ensures that while decoding the encoded message, there is no ambiguity due to the prefix code. Now it simplifies the decoding of message, as this is what I have been stating all the time. So Huffman code is a very important mechanism to code the characters, alphabets. So let's look into the process. Well, Huffman coding process is basically 2-step process. First, we are going to build a Huffman tree, and then we are going to find the Huffman code for each character using this Huffman tree. All right. So 2 steps: building the Huffman tree and then finding the Huffman code for each of characters using the Huffman tree. So let's look into this. Once again, we do this particular building the tree with the help of an example. And whenever we want to do an example, first we must try to identify the process. So this is what the process is. So any process in computer science starts with an input. So a set of m characters. So in our case, they are going to be 100 characters, and each characters, not 100 characters in total, but each character will be related with associated with the frequency, right? So a number of alphabets are going to be just 5 or 6 only. Each character m has a frequency which is a member of the set M, has a frequency which is named, or the variable named m frequency. Okay, And the data structure which we are going to use, we are going to store all the characters in a min priority queue. So data structure is going to be min priority queue, and what you understand, min priority queue is going to have minimum values at the top and bigger values at the bottom of the tree, okay, or at the leaves of the tree. That is how the min queue is going to work. The root is going to be the smallest, and then all the child of the root are going to be larger than the root, and all the child of subsequent childs are going to be larger than the earlier parent of it. Okay, so this is what it is, and we will be coding frequency within those keys. Okay, and this min tree, that is min heap, takes log n. Suppose you want to insert an element in min heap, it just takes of order log n only. So min heap is a very useful data structure which we would like to utilize for developing or for designing this Huffman tree. Okay, so what is the algorithm for building Huffman tree? Well, the algorithm in this particular case is very, very simple. What we are going to do first, since we have created that min priority queue, from that min priority queue, extract two minimum nodes xy. Okay, so from that min priority queue, PQ, make a new node Z with x as a left child and y as the right child. X is going to be the smaller one, y is going to be the slightly next higher in that queue. Okay, and replace nodes xy in the queue with a new tree node Z, and the frequency of Z is the sum of frequencies of x and y, and repeat the steps which are given above until one node is left in the queue, and return this last node in the root as the Huffman tree. Now the whole process looks very, very difficult to understand. Okay, now this whole process is difficult to understand. So how we are going to understand this whole process? Very simply by taking up a simple example. So once again, let us take the example which we were following or which we were discussing and try to make Huffman tree for this particular example. So this was our example, and what is the objective? We are going to build a min priority queue based on the frequency. So initially, what PQ contains? 6 nodes. What are those 6 nodes? What you can see, right? A, B, C, D, E, F, right? But which has the minimum frequency? B. So min priority queue will have B as 2, E as 3, that is next higher, C as 5, F as 7, D as 13, and A as 70. It is in the sequence of their frequency. So now, as per our process, we need to pick up 2 nodes, B as well as E, and make a tree of these 2 nodes. Okay, so this is what we will do. Okay, so we pick up B as well as E. Okay, and make the node, make a subtree Z, right? Make and add Z, you can see in the diagram, right? What is the frequency of Z now? The subtree Z? The B was having frequency 2 and E was having 3. So just add that, 2 plus 3 becomes 5. So Z has become, now this is our subtree now. This subtree has been made, the Huffman node, we have made this subtree, and now this subtree is added. Z is added back to the queue. So what queue becomes now? Queue A, B and E have been removed from it. Z has been added. C, F, D and A remain in that particular queue, right? So this is now our new queue, and we have already started the building process of Huffman tree. Now once again, which are the smallest? Z as well as C. So we will once again take Z as well C. Z is already 5, B2, E3. Okay, now we will couple it with C5. How we will couple it? Now you can see 5, B2, C, E3 is already there. C5 has been added, and now Z is having a frequency of, the 5 was the frequency which was earlier, and 5 is the new frequency. So now it becomes 10. Okay, so 5 plus 5, 10. Now technically this Z10 should be after F7, but for the sake of simplicity we have just put it over there. What is the next pickup of from the priority queue? It's going to be F7 and Z10. Okay, so this Z10, that is the whole subtree, will be picked up with F7. F7 will become the left subtree, right? The smaller becomes the left subtree. So X becomes the left subtree. That is what you can observe in the diagram. So F7 becomes the left subtree, and then the whole subtree of Z became the right subtree, which is shown with the help of Y. And now the Z, the new node Z is 10 plus 7 becomes the 17, right? So now we have added this back to the queue. Now we have D13, Z17 and A70. Okay, so now these three nodes we will pick up. Once again, D13 will be towards the left of this particular tree, right? So you can observe this now. So D13, then earlier one, that is the subtree, was having weight of 17, Z. Okay, now the new Z has a weight of 30, right? So the whole subtree now has been added. Okay, and this Z is now 37 and 70. So now once again we finalize this particular tree, our building of our Huffman tree. The process is now complete. Okay, so now you can see this is the complete, the process has been completed. We have just one node Z in the queue now. Earlier there were many nodes in the priority queue. Now there is only one node, which happens to be the root node. Okay, so we have now created the, or built, we have built the Huffman tree with this particular algorithm. Now once we have built the Huffman tree, what we do next? We got to create the codes. We have not yet created the code in this particular situation. So okay, so what we are going to do, finding the Huffman code for each character, that is going to be the next step. And how do we do this particular thing? Traverse the tree starting from the root node, that was the Z node, which we where the frequency was 100 total. Label an edge connecting to the left child as 0. Label an edge connecting to the right child as 1. Traverse every leaf node in the tree. We have to traverse every leaf node. Huffman code for a leaf node. Actually, you will find that the characters are only at the leaf node, right? Not at the intermediate node, okay? So the leaf node is the sequence of label on the edge connecting the root to the leaf of that particular character. What does it mean? Let's take once again, try to explain it with the help of example of our tree. So finding the code. What was the first step? So we are labeling. You can observe that towards the left of 100 we have put a label 0, and towards the right of it we have put a label 1, right? Towards the left of 30 we have put a label 0, towards the right of it we have put a label 1, right? Towards the left of 17, once again 0, right of 17, 1, towards the left of 10, 0, right of 10, 1, and so is the case of 5. So this is okay. So in every case we have done it. Now let us try to find out the code for, let's say, start the code with A. What is the code for it? So traverse from 100 till A. Only one traversal is there, okay, and that is 1. So this is the first code you can see, okay. So the code for A is just 1, okay. Now next is code for D, right? So 0 followed by another 0, which is the leftmost element you can see, D, right? D13 you can see to the left of 13. So 0, 0. So this is what you can observe. D is, the frequency is 13 and code is 0, 0. Let's now take code for, let's say, B. Okay, B is at the bottom, you can observe. So let's traverse from 100 till B. So it is going to be 0, then towards the right 1, then 1, then 0, 0. So it is 0, 1, 1, 0, 0. Okay, so you can see 0, 1, 1, 0, 0. So now you can traverse all these nodes, right? Similarly, if you see C, it is going to be 0, 1, 1 and 1. So you reach C5. So the code for C is going to be 0, 1, 1. Okay, now How many total characters are needed now if we are coding the overall system with this particular coding mechanism? So you can see it is a variable length coding. Okay, A has the maximum frequency and the code for A is the smallest, right? D has next higher next lower frequency, next higher frequency, and its code is also smaller, right, than others. B has very low frequency, therefore its code is bigger, right? So we have now coded and we have multiplied the code length and the number of characters. Okay, that is 1 into 70, 5 into 2 you can observe in this particular case. B, the size of B is 5 bits, and there are just 2, the frequency is 2. So 5 into 2 becomes 10. So we have done it for every of the character, and what you find now, just 162 bits are needed. Okay, so overall now just 162 bits are needed. In the earlier cases, what we have observed, in the first case, ASCII coding, we needed 700 bits. In the case of just 3 bits, we still needed 300 characters. Over here, it is further brought down to 162 bits. Now, how we are going to encode this particular characters? Okay, so example, like for example, a typical message, we have not included all, but just we are trying to show a simple example with the help of the diagram. Okay, so suppose my message is A, B, E, F, D, A, C. So for A, the code is 1, for another A, code is 1, 1. So you just keep on coding, putting the code, and just club all that information, and you are going to get the overall coded sequence. Now, the important thing is the decoding, right? So, how you are going to decode the string? Now, we have not used the previous string. We have used another string over there. Now, look into 0, 1, 1. Okay, the second string 0, 1, 1, 0, 0. There is no prefix 0, 1, 1, 0, 0 except B. Right? There is no ambiguity. 0, 1, 1, 0, 0. It cannot happen. Okay? Except for B. Okay? Because in C it is 0, 1, 1 and then 1. Right? So it has to be 0, 1, 1, 0, 0. Only code which is possible is B. Next, 1. The only code possible is A. Once again a 1. Another code which is possible is A. Right. So that is the way decoding is going to takes place. Okay. Then 0, 1, 1, 1. There is only one code which is there, which is going to be C. This is going to be followed by 0, 0. Okay. So 0, 0 is only one code which is D, which is once again followed by 0, 1, 1, 0, 1. Which is basically E. So you can refer to that particular code. And then 0, 1, 1, 0, 1. Once again it is E, and last is F. So you could easily decode this particular message without any ambiguity. You can demarcate. You can very easily, your algorithm can demarcate by matching the longest string possible. Okay, matching the longest string possible and then finding the results. For the case of 1, the longest string matching is only 1. You can watch. All other codes are starting with 0. All right. So this is the way decoding algorithm is simplified in this particular situation. Okay, by using the Huffman code, no common prefix situation. Okay, so this is the way Huffman code is utilized and used. Now let us talk about the time complexity of Huffman code algorithm. Well, since we are using a priority queue, right, for binary min heap, so building min heap procedure will take order n time. Okay, minimum that order would be needed. The tree is taking exactly, tree is made exactly n1 minus 1 time, because every time we are extracting 2 nodes and putting back 1 node. So n minus 1 times we are executing. Since each step a new node z is added to the heap, when a new node is added, it takes order log n time only, as we have discussed earlier. Thus the total running time for Huffman code on a set of n character is order n log n only. not more than anything. Okay, so this is a very, you can visualize that Huffman code is a very efficient process, right? So you can create code very easily, and decoding process is also very, very simple. So we must use, and obviously it is a good compression standard. So if we like to summarize the whole thing, Huffman code is an approach to compress data when the frequency of each character is different. Okay, it is a variable length code. It is not fixed length code. Every character has a separate length. The prefix of the code of two characters is kept different to ensure unambiguous code decoding. This is very, very important, because if we are not able to create unambiguous decoding, we are going to have lots of problem in decoding the message. Okay, the algorithm involves making a Huffman tree followed by generation of code. The algorithm running time is of the order n log n, which is very, very efficient. Okay, so Huffman coding is one of the good compression standard when we are transmitting digital character data, as it does this particular, but the frequency of characters should be different in that particular case. If frequency of all the characters is same, then there is no point doing any coding with the help of Huffman coding. If whatever characters which we are transmitting have different frequency, which is normally the case when you are creating textual documents, then Huffman code is the right kind of coding standard which you should be using. With this, we end this particular session. Thank you for being with us.